Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over how to write molecular, complete ionic, and net ionic equations of weak and strong acid-base reactions. And in this video we're going to go over sodium hydroxide with hydrofluoric acid. So let's get into this. So we have sodium hydroxide. Sodium hydroxide is a strong base, and we have hydrofluoric acid, and hydrofluoric acid is a weak acid. And so this is going to be, we're going to need to make sure we pay attention to the fact that this is a weak acid when we're writing uh, our net ionic equations, because this is kind of reaction where students kind of go astray and they make mistake here. And even teachers will make mistakes here as well. So this, I think, is going to be an insightful video. So here we have a strong base, and again, you have to know what the strong acids and strong bases are. There's only 6 strong acids, so you should know those. Anything that's not one of those 6 is going to be a weak acid. And again, there's only a certain number. There's only a certain kind of hydroxides that are going to be strong bases. So usually it's your group 1 metal hydroxides and your group 2 metal hydroxides, um, or at least some of them. So you should know what those are so you can identify them right away. The reason for that is because when you're writing your net ionic equation, it's going to be important to know whether you have a strong acid or a weak acid, or a strong base or weak base in the reaction. Okay, so here we have a strong base. It's going to be an ionic substance. So the way we write the formula, you're going to have to go from the names to the formula. So you got to know how to name your acids, and you got to know how to name your bases. So here we're going to go backwards. The name of your strong base, it's an ionic compound, so we can work backward from the name. And the 2 parts of the name give you the 2 ions. So we know we have a sodium. So sodium is Na, and there's a plus charge on sodium. And the way you know that there's a plus charge on sodium is a couple of different ways. First, you can know it by the fact that it's in group 1, and we know that the group 1A elements are going to have a +1 charge. And there's a general rule for that. If you're in the main group elements, groups 1A through 3A, then the positive charge of the ion will be equal to the group number. So if you're in group 1A, then you're going to have a +1 charge. If you're in group 2A, then you're going to have a +2 charge. And if you're in group 3A, you're going to have a +3 charge. Okay, so since we know that sodium is in group 1, we know it has a +1 charge. The other way that you can know is by paying attention to the number of valence electrons that you have, and the structure of the atom. We know that all atoms want to be like noble gases in that they have a full outer shell, right? So the number of valence electrons will help us to determine whether they're going to gain or lose electrons. So if, again, we know that the number of valence electrons of an element in the main group elements are going to be equal to the group number. So if you're in group 8A, then you have 8 valence electrons. If you're in group 5A, then you have 5 valence electrons. And so here again, we know that it's in the sodium is in group 1A, so it has 1 valence electron, and it wants to have a full outer shell. Now that sodium could gain 7 electrons and get a full octet with an outer shell, or it can just lose that 1 electron and have an outer shell after losing that electron. So it's easier to lose the 1 electron than it is to gain 7. So it's going to lose that 1 negative electron. And so when it does that, there's going to be a proton that is no longer balanced by the negative. So you're going to have a positive proton that is no longer balanced by a negative electron, and that's where the positive charge comes in. So here we have a +1 charge. Your hydroxide, that is a polyatomic ion, so you have to know your polyatomic ions. I'm sure your teacher gave you a polyatomic ion sheet. Check out my video on polyatomic ions. I kind of help you to memorize them. I give you patterns that can help you memorize the polyatomic ions. So if you're interested in that, you can go see my video on polyatomic ions. But here we need to know that hydroxide is an OH minus ion. And so once you know the ions and their charges, you put them together in a formula and you want to balance the charge. So here we have a +1, here we have a -1. And so we only need one each to balance the charge. So we could write our formula. You could also do the crisscross method, right? So if we have a 1 here and a 1 here, then we could put one subscript there and this one would be a subscript there. So it's 1 to 1 again. So then our formula would be NaOH. So that's the sodium hydroxide. And then what about hydrofluoric acid? So you want to recognize the type of acid you have here. And so there are two types of acids, your oxyacids and your binary acids. And a dead giveaway of your binary acid is the fact that it's going to begin with hydro. So here you have hydro. So this is not an oxyacid. So you're not going to have a polyatomic ion with oxygen in there. So hydro, you can remember hydro by the fact that hydro refers to having hydrogen in your molecule since this is an acid. So hydrogen comes first, and fluoric comes from the fact that the other element, remember binary means two, so you're going to have hydrogen plus another element. And so you're going to have fluorine. So fluoric comes from fluorine, so you're going to have HF as your acid. So HF is the acid. So here we got our base and our acid. And so now we want to put those together and we want to form products. So here, the great thing about your acid base reactions is that you could treat them as a double displacement reaction because this is an ionic substance and it's not an ionic substance, it's a molecular substance that can ionize into ions. And so we could treat it like an ionic substance. And so whenever you have two ionic substances as reactants, that's a dead giveaway that you have a double displacement reaction. So this will behave like a double displacement reaction. So how do you find the products of a double displacement reaction? You put the inside ions together and you put the outside ions together. So the sodium and the fluoride ion will come together. So you have NaF because the fluoride ion is a -1 and the sodium is a +1. So you need one each to balance the charge. And so then you have the H and the OH. The H plus will go together with the hydroxide ion, and that gives you water. So you get plus H2O. And so here, now we have our equation. We need to make sure it's balanced and we need to make sure we have the right states. So here we have one sodium, so that's balanced. We have one hydroxide and one hydrogen that forms one water. So we have one water there. And then we have our fluoride, one fluoride ion, one fluoride ion. So this is a balanced equation. What about the states of matter? So your acid and base are going to be normally aqueous. So we know that this is aqueous because you can look at your solubility chart, your solubility rules. I'm sure your teacher gave you a chart, or you can easily look it up on the internet. If you look up hydroxides, you'll find that all hydroxides are going to be insoluble unless you have a group 1 metal and heavier group 2 metals. So this one is going to be soluble, so that's aqueous. And then you have hydrofluoric acid. And so your hydrofluoric acid is going to be aqueous as well. I'll come back to hydrofluoric acid in just a moment. We got to recognize that this is a weak acid. And so there's something special about that we need to keep in mind. So again, your sodium fluorides, is that aqueous or is that a solid? What's going on here? So if we look up in your solubility rules, it says all fluorides are soluble except for group 2 elements. So magnesium, calcium, strontium, barium, and lead 2 ions We don't have that. We have sodium, which is a group 1. So that is going to be aqueous. So that is soluble in water. And then we have liquid water. So that is going to be liquid. Okay, so here we have our balanced equation with the states of matter. So this is our balanced molecular equation. Now we're going to do our complete ionic equation, and this is where you need to be cognizant. You need to be aware of the fact that you have a weak acid here. What is the difference between a strong acid, weak acid, or a strong base, weak base? Well, strong bases and acids are such that when you put them in water, they will dissociate or ionize into ions. So here we have a strong base. So when you put this in water, these ions are not going to stay together. So practically 100% of this is going to dissociate into its separate ions. So you're not going to have this actually in solution. These are going to actually be separated. So when we write our complete ionic equation, we're actually going to separate those because that's how they actually are in solution. Here we have a weak acid. Okay, the distinction again between we talked about the distinction what a strong acid and base are. So strong acids and bases are going to dissociate or ionize completely in water, 100% practically. What about weak acids and bases? Well, weak acids and bases hardly ever dissociate or ionize in water. So very, very little of that molecule or formula unit is going to dissociate. So most of the species that's in your water is going to be together in this formula. So since this is a weak acid, what's actually in solution for the most part is the HF molecule. So this HF molecule is together and it's dissolved in water. So you have HF molecules floating around in water. You don't have H plus and F minus floating around. You do, but it's a very, very tiny bit compared to the amount of HF you have in water. So this actually stays together in water for the most part. There's a tiny bit that will dissociate or ionize into your H plus ion and your fluoride ion. So we need to represent that in our complete ionic equation. So when we do that, so this is going to dissociate. So we're going to write our ions. So we're going to have Na plus aqueous. And so when we're writing our complete ionic equation, anything that separates into ions is going to be separated, and you're going to write it as the ion with the charge. So now you're going to write the charge. So when you're in the molecular equation, the reason we call this a molecular equation is because even though these are ions, we're writing them as if they're molecules. But now we're writing the ions separately. So anything that's aqueous and separates is going to be separate. So here we have Na plus aqueous plus OH minus aqueous. And then normally, if this was a strong acid, we would write these separately. The H plus would be separate and the fluoride would be separate, but this is not a strong acid, it's a weak acid. So we're going to keep this together. So this is going to be plus HF aqueous. So here we have our acid. So now we're going to do the same thing. We're going to write our products over here, and we're going to separate the products if they're ionic, and we're going to keep the water together. So anything that's liquid, solid, or gas, we're going to keep together. And so here, the sodium fluoride, that's an aqueous solution. This is soluble in water, so that's going to be separate. So again, we're going to have our Na plus aqueous plus our fluoride ion, aqueous. Okay, and so we do have a fluoride ion. Why? Because some of the HF is going to go, separate. Okay, So this is going to separate a little bit. So we do have a reaction going on. Your strong base is going to react with the weak acid. So we're going to get our F minus here. And then we're going to have our H2O liquid. And so let's double check. And so here we have our balanced, our complete ionic equation. The water's together. These are separated. This stays together, and these are separated. So this is our complete ionic equation. Let's double check. Okay. So now I hope this makes sense to you, why this stays together. Now, when we do our net ionic equation, we're going to only write net ionic equation. So when you're writing your net ionic equation, you got to remove what are called the spectator ions. And the spectator ions are those ions that are not part of the reaction. And so a couple of things, ways you could figure out what the what the spectator ions are is by one, you could look at what products are being formed. So we have water, right? So water is being formed here. And then whatever's not part of that would be the uh, whatever's participating in forming that product. Those are not going to be your spectator ions. Anything else would be spectator ions. Now that normally works, but in this case, if you went that route, you would go astray because you would be missing out on the fact that this is a weak acid. So the better way to go about this is to look at what changes and what stays the same. If anything stays the same on both sides of your reaction, if they stay the same state or anything like that, if everything stays the same, then you know it's a spectator ion. If something changes, then you know it's a player. It's part of the reaction. So, for example, you can see in the sodium ion, it's Na plus aqueous over here, and it's Na plus aqueous over here. So that would be a spectator ion. It's not involved in any reaction. There's no change in that ion. So you can get rid of that. What about the OH minus ion? So OH minus is aqueous over here, but it's been absorbed and combined with H plus to form water. So that is a change. So we're going to keep this one in the net ionic reaction. What about HF aqueous? So we have HF aqueous over here, but we don't have HF aqueous over here. So there is a change. So we're going to keep this in our net ionic equation. And of course, here we have fluoride ion here. We don't have a fluoride ion over here, so that's a change. So we have the fluoride ion here, but it's really not the fluoride ion. It's part of the molecule here. But the fluorine atom ionizes to become the fluoride ion, so that is a change. So we're going to keep the fluoride and, of course, the water. Okay, so that would be our net ionic equation. When we write that out, it's going to be OH minus aqueous plus HF aqueous, and that gives you F minus aqueous plus H2O liquid. And so this is your net ionic equation. And so you got to be very careful and pay attention to whether or not you have a weak acid or a weak base, because those weak acids and weak bases will stay in the net ionic equation. So it's very easy to assume that, since I have a strong base here, it's going to react completely with the HF, and so then all of this is going to be water. So it's going to be H plus OH minus gives me water. And that would be true if it's a strong acid with a strong base reaction, but it's not. So it's not going to, our net ionic equations or our ionic equations are not going to have that format there. So I hope this was helpful. I hope that clarified everything. I'll have more videos going over more examples. So stay tuned. If you like this video, if you learned something from this video, please hit the like button, make a comment in the comment section. Let me know what you think. And if you have any other questions, and please subscribe to my channel, hit that button up there for the notifications. And thanks for joining me. Have a great day.